Alright, in this video, we study positive definite matrices as opposed to positive semi-definite matrices. A symmetric matrix is called positive definite if all of its eigenvalues are strictly positive. And if matrix A is positive definite, we write A greater than 0. The goal of this video is to show that a positive definite matrix induces a kind of inner product, an inner product that is very similar to the inner product we have been studying so far. And this inner product will serve as a basis for the kernel method, which we will see in future videos. Okay, let's start. Okay, first, a definition. For a given positive definite matrix A, we define the positive definite inner product of vectors x and y with respect to A as this. So this is the new inner product we are defining. And here we have A here. And this is the inner product we have been studying so far. Of course, A is a symmetric matrix by assumption. And so this is, of course, equal to x times A, y. So the place of A doesn't matter. Of course, we can define anything and call it an inner product, but that naming is not arbitrary, actually, and we call it an inner product for a reason we now discuss. Now, here are some of the properties of the positive definite inner product. In fact, these are the properties that can be considered as a set of axioms for the inner product. And because of these properties, we call this positive definite inner product as inner product. Okay, I think most of them are quite trivial. For example, this one is equal to, just go back to the definition, ax times y plus z. And from the property of the usual inner product, this can be split into two parts. And ax, z, but this is x, y, a, x, z, a. And this one is more or less the same. And this one is also trivial, I think. And for this one, x, y, a, according to the definition, this is a, x, y. But since A is symmetric, we have x, a, y. And the inner product is commutative, therefore we have a, y times x. This is equal to y, x, a. And this one is also trivial because A is positive definite, and any positive definite matrix is, of course, positive semi-definite. And this is one of the conditions that defines a positive semi-definite matrix. So this is trivial. Now let's show this part 5. So first, let us assume this spectral decomposition. And since A is assumed to be positive definite, all of the eigenvalues are positive, strictly positive. Okay, so if we take this inner product, by definition is this, and apply this spectral decomposition, and we have this. And again, this part is the inner product, the usual inner product. As this, so we replace this with this, and this is now a constant, so we can take it out. Now we have uj times x and uj times x, so it's uj x times uj squared. Therefore, this is always positive or 0, but since we are assuming all of lambda j's are strictly positive, so if this is equal to 0, that means this must be equal to 0. So the inner product between x and uj is equal to 0 for all uj's. Now, since the eigenvectors, the set of eigenvectors is an orthonormal basis of the vector space, any vector x can be represented as a linear combination of these eigenvectors, like this. Now, take the inner product between x and ui, the ith eigenvector. Since we have this equal to 0, and from this expression we have this is equal to ai, that means ai is equal to 0. And this holds for any I. So a1, a2, and so on up to an, they are all equal to 0. That means x is the 0 vector. So we have shown that if the inner product between x with itself is 0, then x must be the 0 vector. And the converse is obvious, because if x is 0, then the inner product between x and x is 0, obviously. So we are done. Now, just like the inner product induced a norm, this positive definite inner product also induces a norm like this. So we define a norm like this. And here's a rather trivial theorem. If alpha is any real number and x is any vector, then the a norm of alpha x is equal to the absolute value of alpha times the a norm of x. And it is an exercise for you to prove this. The next theorem is the very familiar Cauchy-Schwarz inequality, but in this case for the positive definite inner product in the norm. And to prove this, the proof of this is exactly the same as before, because in order to prove this inequality, we didn't need any specific details about the definition of the inner product. All we need was the basic properties of the inner product, which we proved in theorem 1. So proof is exactly the same as before. For any real number t, we calculate this quantity, tx plus y, norm squared, and which can be expanded as this. Now we have a quadratic form in t. But this must be greater than or equal to 0 because it's a real number squared. Therefore, the discriminant of this quadratic form must be non-positive. And that's what we have here. And from this, it's immediate to have this inequality. And we are done. So we may consider the Cauchy-Schwarz inequality as a generic feature of any inner product that satisfies the basic properties, as we have proved in theorem 1. And again, from this inequality, we may define the distance or the angle between two vectors with respect to A. That is the angle, for example, between the two vectors. Let's call it theta A as the inner product x and y, A and the norm of x, A, and the norm of y, A. So this defines an angle between two vectors, but this is modulated by the matrix A. And from the Cauchy-Schwarz inequality follows the triangle inequality, just like before. And by now, the proof should be trivial and it's left as an exercise. Finally, let us discuss briefly the relationship between positive definite matrices and the kernel method. First, let's regard the vector x, made of these numbers, as a function from the finite set consisting of n integers to real numbers. That is, when we apply this function x to the integer 1, we get x1, and so on. And if we apply this function to the integer n, then we get xn. So this defines a function. Okay, now let us define these orthonormal basis vectors. That means ej means only the jth element is 1 and everything else is 0. And define this vector kj. by some, A is of course a positive definite matrix, so its inverse exists because no eigenvalues are 0. And A inverse times EJ is KJ. So now let's consider this positive definite inner product between X and KJ. And by definition, we have this, and because A is symmetric, the place of A can be swapped, but the KJ is A inverse EJ, so A times this is just EJ. And if we just multiply this, these two vectors, then we get only the jth element of X, which is XJ. XJ is of course XJ. So what this tells us is that function application can be considered as an inner product. This change in the point of views is the first step towards the kernel method. And by the way, this KJ is called a reproducing kernel, and the vector space equipped with the positive definite inner product, where a reproducing kernel always exists, is called a reproducing kernel Hilbert space, RKHS, which we will be studying in future videos. Okay, that's all for this video. See you later. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.